Every year, billions of pounds of plastic waste travel through America's rivers and waterways before reaching the open ocean. Most of it moves unnoticed, carried by stormwater runoff, pushed along by seasonal floods, tumbling over weirs and through drainage channels in cities where the infrastructure was never designed to catch it. For decades, the only line of defense was manual cleanup. Crews in boats, volunteers with nets, and municipal workers pulling debris from shorelines by hand. It was slow, expensive, and never enough. But starting in 2014, a different approach began to take shape in Baltimore's Inner Harbor. It didn't rely on volunteers or municipal budgets. It relied on a water wheel, a conveyor belt, and the current of the river itself. The machine was called Mr. Trash Wheel. It was deployed in May of that year at the mouth of the Jones Falls River, where decades of urban runoff had turned the harbor into a floating landfill. The design was deceptively simple: a 14-foot steel water wheel mounted on a fixed platform, turning with the flow of the river, and powering a raking system that lifted debris off the surface and onto a conveyor belt. That belt carried the waste up and into a waiting dumpster barge. When river currents slowed, during dry spells or calm weather, 30 rooftop solar panels kicked in, pumping water to keep the wheel turning. The system ran day and night, in rain and heat, with almost no human intervention. It worked, and it kept working. Over the following years, Baltimore expanded the program. A second unit, Professor Trash Wheel, was installed nearby. Then Captain Trash Wheel, then Gwinda. Each was positioned at a key outflow point, catching waste before it could spread across the harbor. By 2024, the Trash Wheel family had collectively removed more than 5.2 million pounds of debris from Baltimore's waterways, including 1.8 million plastic bottles. The numbers alone told a story that years of policy debate had not. Stationary interception at choke points could remove staggering volumes of waste with minimal operating cost. But Baltimore's harbor is a calm, controlled environment. The water wheel design depends on predictable currents and relatively narrow channels. Scaling that concept to larger, faster, more unpredictable waterways required something different entirely. In October 2022, a new machine arrived at Bologna Creek in Los Angeles. It was called Interceptor 007, and it was the first deployment of its kind in North America. Where Mr. Trash Wheel was compact and mechanical, the Interceptor was industrial. It was a 70-foot-long solar-powered catamaran anchored in the creek channel, using a V-shaped boom configuration to funnel surface debris toward its intake. As trash accumulated, an automated system distributed it across 6 internal dumpsters, housed on a detachable barge. When the barge was full, it could be towed away and replaced without shutting the system down. Bologna Creek presented a challenge Baltimore never had to face. The creek drains a massive urban watershed, and during storm events, peak flows can reach 18,000 cubic feet per second. The Interceptor had to be engineered to withstand those surges, not just to survive them, but to keep collecting through them. Structural resilience became as much a part of the design as the collection mechanism itself. Over its 2-year pilot program, Interceptor 007 captured 248,648 pounds of material, 124 tons. That figure included everything from plastic bags and food wrappers to shopping carts and construction debris. Of that haul, 2,738 pounds of recyclable plastic was diverted for reuse. The rest, heavily contaminated by the mixed composition of urban runoff, followed a different path, one that raised its own set of questions about what happens after collection. While the harbor machines and creek interceptors focused on flowing water, a separate problem was growing across the Great Lakes. An estimated 22 million pounds of plastic enters the Great Lakes system every year, and much of it washes ashore. It buries itself in sand, breaks into smaller and smaller fragments, and works its way into the substrate of public beaches and protected shorelines. Cleaning it by hand is labor-intensive and often ineffective at catching smaller particles. The response came in the form of a remote-controlled beach robot called the Bee-Bot. Roughly the size of a compact utility vehicle, the Bee-Bot rolls across sand and sifts it to a depth of 4 millimeters below the surface. It separates out plastic fragments, cigarette butts, bottle caps, and other small debris while leaving the sand and natural material behind. Its operational capacity allows it to clean up to 3,000 square meters per hour, and its design avoids the kind of heavy disruption that causes shoreline erosion. It does not dig, it sifts. The distinction matters on fragile lakefront ecosystems, where the margin between cleanup and damage is thin. On the water itself, a different tool took over. The Pixie drone is a small mobile floating collector with a 160-liter capacity and a battery life of 6 hours. It moves across the surface of harbors, marinas, and nearshore areas, skimming debris that the larger interceptors cannot reach. It is not designed for volume. It is designed for access, getting into shallow coves, around docks, and along irregular shorelines where fixed systems cannot be installed. Together, the Bebot and the Pixie drone addressed something the earlier machines could not: the diffuse, scattered plastic that doesn't follow a single current or flow toward a single choke point. It spreads, it fragments, and collecting it requires machines that can move with it. That principle, mobility over fixed interception, became the foundation of the next generation of cleanup technology. The ClearBot Neo is a 3-meter-long autonomous surface vehicle powered by onboard AI. Its cameras identify floating trash with 95% accuracy, allowing it to distinguish between waste and organic material in real time. A single unit can collect up to 500 kilograms of waste per mission, or roughly 1 metric ton per day. It doesn't need an operator on the water. It navigates, collects, and returns on its own. What makes the ClearBot unusual is not just the machine itself, but the business model around it. It operates on a robot-as-a-service framework, meaning cities don't need to purchase and maintain individual units outright. They deploy fleets on contract, at what the developers claim is a 50% reduction in cost compared to diesel-powered collection vessels. The units are modular too. Depending on the attachment, the same platform can be configured for oil spill recovery at a rate of 15 liters per day, or for the removal of invasive water hyacinth, a plant that chokes waterways across the southern United States and much of the developing world. The concept of deploying fleets of small autonomous vessels rather than relying on a single large machine changed the math of urban waterway maintenance. But autonomy on open water brings its own set of engineering problems, especially in crowded harbors and mixed-use waterfronts. That is where the Waste Shark entered the picture. Nicknamed Gulp, the Waste Shark was deployed along New York City's Hudson River Park shoreline, where it navigates using LiDAR imaging and GPS waypoints. LiDAR, a laser-based scanning system, builds a real-time 3-dimensional map of the surrounding environment, allowing the machine to steer around boats, pilings, kayakers, and other obstacles without human input. It collects up to 500 kilograms of debris per day, running on zero-emission electric propulsion that was specifically designed to operate quietly enough to avoid disturbing local wildlife. In a waterfront park shared by joggers, ferry commuters, ducks, and swans, noise and disruption are not minor concerns. They are design constraints. The Waste Shark also found a commercial market beyond municipal use. Private entities, including Disney and Universal in Orlando, adopted the machines to manage pyrotechnic debris from nightly fireworks shows and to control algal blooms in their resort waterways. What began as a public infrastructure tool became a dual-use platform, serving cities and private operators for different reasons, but with the same core technology. Across all of these systems, one challenge remained consistent: what sits just below the waterline. Floating booms, the barriers used to funnel trash toward collection points, are effective on the surface, but plastic doesn't always float. Waterlogged bottles, dense packaging, and heavier fragments often travel suspended a foot or two below the surface, invisible to cameras and out of reach of surface skimming conveyors. The engineering response was the addition of 2-foot underwater skirts, roughly 0.6 meters deep, attached to the underside of floating booms. These skirts extend the capture zone downward, intercepting suspended plastics that would otherwise pass beneath the barrier. Field data from multiple deployments showed a collection ratio of 99.9% plastic to 0.1% incidental biological catch. The system was pulling trash, not fish. Still, the water itself pushed back. In marine and estuarine environments, Wave action reduced robotic collection efficiency by up to 40%. Machines calibrated for rivers and harbors struggled in open or semi-open water, where currents shift and surface conditions change by the hour. That limitation placed a hard boundary on where these systems could operate effectively, and where they could not. What the machines did collect, however, carried information. Every piece of trash picked up by the autonomous fleets was logged automatically. GPS coordinates, material type, estimated weight. Cameras linked to research institutions, including the Benioff Ocean Science Laboratory, identified and categorized waste in real time. Over months and years, this data built a map, not just of where trash accumulated, but of where it came from, what it was made of, and how its composition changed with weather, season, and upstream land use. That data fed directly into policy. In Maryland, tracking information from the Trash Wheel program contributed to an 85% reduction in foam litter after targeted legislation restricted its sale and distribution. The machines didn't just collect waste. They generated evidence, hard numbers tied to specific locations and specific materials, that made the case for intervention upstream at the source. The shift from reactive cleaning to proactive management depended on that feedback loop. Predictive analytics and waterway mapping allowed operators to anticipate where debris would accumulate before it arrived, repositioning machines and adjusting boom placements based on weather forecasts and flow projections. Cleaning became less about chasing trash and more about intercepting it. But collection is only half the problem. What happens to millions of pounds of wet, contaminated, mixed material river plastic after it comes off the conveyor belt is a question that doesn't have a clean answer. The material pulled from urban waterways, classified broadly as mixed municipal plastic waste, carries heavy contamination. Food residue, chemical runoff, biological matter, and prolonged water exposure degrade the plastic to the point where conventional recycling is often not viable. In Baltimore, the primary disposal method became waste-to-energy incineration. The plastic was burned to generate electricity, a solution that avoided landfilling but raised separate questions about emissions and long-term sustainability. At Bologna Creek, operators managed to divert a small fraction, those 2,738 pounds of recyclable plastic, for reuse. But the bulk of collected material posed a harder problem. Roughly 25% of the average haul consisted of organic matter, leaves, branches, algae, food waste, that had to be separated at specialized materials recovery facilities before any plastic processing could begin. The bins themselves were designed with perforated walls to drain excess moisture during transport, reducing weight and controlling odor. It was a practical solution to a logistical headache, but it underscored a reality. Pulling plastic from a river is not the same as recycling it. The organizations behind these machines are not treating them as isolated projects. The long-term strategy calls for deployment in 30 major coastal cities by 2030, with target locations in the Americas, including Los Angeles, Panama City, and Montego Bay. The ambition goes further. The goal is to place interception systems in 1,000 of the world's most polluting rivers, waterways identified as responsible for 80% of the plastic that flows into the ocean each year. The stated endpoint is a 90% reduction in floating ocean plastic pollution by 2040. Whether that target is reachable depends on variables that no single machine or fleet can control. Funding cycles, municipal cooperation, material processing capacity, and the sheer volume of plastic still entering the waste stream every day. The robots are in the water. The question now is whether the systems around them can keep up.